In this section there's two questions that are very similar. I'm going to do question 12, but have a look at the answer for the previous question in the work solutions that are on Canvas, because they are very similar. You'll be able to follow them, I think. So I'm just going to do this one. So first thing it's asking you for is is for dy dx. So we're going to need to differentiate with respect to x the two sides of this equation. So it looks like that. So once we've done that, the next thing we have to do is actually do the differentiating. So to do that, we look at the two parts here, which we can see are a 2x and a y. And this is going to be easy enough, and so is that. So we'll do that. So differentiating x squared, it becomes 2x. Differentiating this thing, oops, we're going to do this, put a negative outside. We're going to do this one part at a time. So derivative of 2x is 2 times y, plus derivative of y is y dash, or dy dx, times 2x. I left the negative outside, you'll notice, because then it means I'm not going to forget it when I'm doing my algebra. And here I've got 2 coming down, so it becomes 4y. Remember there's no x there, so it's dy dx, and 0 on the right side because it's a constant. So I'm just going to expand this negative through here. So I can see now, oops, that I've got 2 dy dx terms on the left side and nothing on the right side. It's a bit boring. So I'm going to take dy dx. I'll actually take all the dy dx stuff to the right side. So all the signs change. I'm then going to factor dy dx out as common. And then the last thing that I'm going to do is solve for dy dx, which is 2x minus 2y on 2x minus 4y. Now the next thing is so that's done. The next thing is to find the coordinates at each point on the curve at which the tangents are parallel to the x-axis. Now the tangents, remember that a tangent line is y equals mx plus c, where m is dy dx. And in order for this tangent to be parallel to the y-axis, remember the x-axis, it's going to be horizontal. So that means that your derivative is 0, or your m is 0, because you want to have a flat line. So what we're going to do here is we're going to, for part B, set the derivative, which is m, equal to 0. So when we do that, you're going to get 2x minus 2y on 2x minus 4y equals 0, which implies that 2x minus 2y equals 0. So that means that x equals y. That's weird because we're used to getting like a value, to put in as m. So because we're getting x equals y, what we have to do is we have to figure out what those values are by putting them into our original function up the top. So I'm actually going to let all the y's in that function equal x. So I've got x squared minus 2x times y. Now instead of y, it's now x. So it's actually going to be an x squared here. Plus 2y squared, that's 2x squared, equals 4. So I can see that I end up with x squared equals 4. That tells me that x is plus or minus 2, and those values will then go into here. So that's telling me that the points happen at x equals plus or minus 2, and because x equals y, those coordinates would be 2 and 2, so that would be implying that x is 2, y is 2, and x is negative 2, y is negative 2. So what does that mean? Well, that means that when we substitute these points into this gradient function, we get 0, and that makes sense because the 2's would make it 4 on the top, 4 minus 4. And these points work because these are points that satisfy the original equation, the actual equation of the curve. So not only are these points where the derivative is 0, they're points that sit on the curve x squared minus 2xy plus 2y squared equals 4. So that's why we don't have lots and lots of points, only these 2 points, which we found by substituting x equals y, which we got from setting the derivative equals 0, into the original equation and solving for x.